So this presentation is going to give you a brief overview of truth tables and logic expressions. So this presentation is going to show you how to make a truth table, write a sum of products logic expression, create a truth table from that logic expression, and then how you could also do it from design specs. All right. So a truth table shows all the possible outputs in response to the inputs. The logic design will have how many ever inputs there are. You'll take it 2 to that power. So if there's 1 input, 2 to the 1 is 2. If there are 2, you'd have 2 to the 2, 2 squared, that'd be 4. 3 inputs would be 2 to the 3rd, or 2 cubed, that'd be 8. You get the idea. The inputs are listed in counting order, starting with 0 and going to either 1 or 4 or 1 or 3 or 7 or 15, whatever you need. All right, and the outputs are listed in the column on the right, and logic circuits may have more than one output. All right, so this is a truth table. All right, so we have our inputs first, then the right-hand column is our output, and there are 3 inputs in this one, and we've labeled them X, Y, and Z. All right, so we have 3 inputs, so we have to have 8 combinations, 2 cubed. So we start with 0, we end with 7. So the first one is 0, 1, 2, if we just look at X, Y, and Z. And then that output, called F1 here, whatever it is just whatever the response is to those inputs. All right. So here's some examples for 2 inputs, 3 inputs, and 4 inputs. If we have 2 inputs, we have 4 combinations. 3 inputs, we have 8. If we have 4 inputs, we have 16. So if we had 5 inputs, we'd have 32. You get the idea. 6 inputs, 64. On and on and on. All right. So what we do is we have to take we can take the logic expression from the truth table. So how do we do that? So we look at the truth table, and everywhere there is a 1 in the output column. What's the output column here? It's the one labeled F5. Everywhere there's a 1 there, we write the expression, okay? So if that input has a 0 in it, the value is not. So we write the not bar over it. All right, so the first place there is a 1 would be where X is 0, Y is 0, Z is 1. Not X, not Y, Z. The next place there is 1 would be at 0, 1, 1. So that would be not X, Y, Z. The next place there's a 1 would be at 1, 0, 0. So that'd be X, not Y, not Z. And then the last place there's a 1 would be at 1, 1, 0. So that's X, Y, not Z. All right, so we take those, all those are called min terms. That's not super important for you to know. And then we add them up, we sum them. So if we add them, right, we need to use an OR gate. That's the equivalent AOI expression. All right, so we would say that is not X and not Y or Z and Z, or not X and Y and Z, or X and not Y and not Z, or X and Y and not Z. And that is our sum of products logic expression. It's a sum. We add up the products. Sum of products is where that comes from. All right, so here we go through and do it the exact same way. So here we have a 1. So we have to write the expression for that. It's not A, not B, not C, and D. This one is, the next line is not A and not B and C and D, and on and on. So we end up, we have 1, 2, 3, 4, 5 1s in the output, and then so we have 5 terms in the expression, 1, 2, 3, 4, 5. So you can see how they match up. All right. So we can also go back the other way. We can take the expression and write the truth table for it. So everywhere we find an expression, we plug it in. So this one says it's not X and not Y and not Z. Well, that's 0, 0, 0. That's the first line. Put a 1 there. Then let's do this last one. It's not X and Y and Z. Not X and Y and Z. Right there. Now this one only has 2. It says X and Z. So we'll get to later where that came from. But basically, since there's nothing about Y there, we don't care what Y is. So anywhere X is 1 and Z is 1, we'll put a 1. It doesn't matter what Y is. That's why Y is omitted. All right? So now you can pause this and try to make the truth table from this logic expression. All right? So you know you're going to have one for this one. You're going to have one for this one. But this term and this term are both going to generate more than 1, 1 in the truth table. So here is the truth table. You'll see not A, not B actually ends up making 4 1s in the truth table. These each make 1, and B, not C, and D makes 2. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8 1s out of 16 possible. Alright, so I hope this helps, and that's a little introduction of logic expressions and truth tables.